Hello, and welcome to the second lecture in the Jabrah Reinforcement Learning series. In this lecture, we're just going to go through some of the important and basic concepts as well as notations that we'll be using in future lectures. So, this lecture is not going to be so detailed, we're just going to focus on uh, an overview of what we need to know in order to solve for these problems. The main focus of this lecture actually is going to be on Markov Decision Processes, also known as MDPs. So what are Markov Decision Processes? Well, these are like the mathematically idealized version of solving for reinforcement learning problems, right? So what that means is that imagine you have a model of the environment. So that means that you know that if you perform this action from that environment in a certain state, it will lead you to another state with this much probability and so forth and so forth. So you understand how the environment dynamics actually work and how any changes uh, to the environment or any actions rather that you take in this environment, like where would they lead you and with what probability. So if you don't understand what that means right now, that's perfectly fine. That's what we'll be explaining anyway in this lecture and future lectures, as this is uh, the underlying point behind reinforcement learning problems. So to start, we're gonna go back to our simple diagram that we showed in the previous lecture, where we have an agent and we have the environment, right? So, like we say that the whole point of reinforcement learning problems are just an interaction between the agent and the environment it's in. And we showed in the last lecture what examples of what an agent might be, what the environment might be, and so forth. And we'll show more examples as we go on. So, what can the agent do, right? The only thing that the agent can do is take an action, right? The agent takes an action, AT, and based on what action the agent takes, the environment will reward the agent at time step. We'll just say RT plus 1. Well, I'll explain what this means. This should be reward. And also put the agent in a new state, ST plus 1, assuming that the agent started at state ST, right? So the agent started at state ST, he took an action AT, and then got rewarded at RT plus 1 and ended up at a new state ST plus 1. So this interaction kind of continues, like, okay, I'm at some state, I take an action, I get a reward, end up in a new state, I take an action, get a reward, end up in another state, and it continues until the end of what we call the episode, and this happens in time step capital T, so ST. This is how we represent what we call the terminal state. Again, it's fine if this doesn't make sense right now. I'm gonna explain what I mean by all this. So to actually understand what's happening here, first let's actually draw the timeline, right? So we have time step 0, time step 1, time step 2, time step 3, all the way up to time step n. Okay. So at each time step, the agent needs to make a decision, and at each time step, the agent ends up in a new state. So imagine it in the following manner, like at time step 0, you need to make a decision about something. It can be anything, and this decision is what we call an action. So you make your decision, right? Let me use a different color for this. So you need to make a decision, right, which we'll call A0, right? You need to make a decision. After you make a decision, depending on whether it was a good decision or not, you get some reward, which we call R1, and end up in a new state, which we call S1. This is at time step 1. Now you're at time step 1. You need to make another decision, right? So you make a decision which we call A1, and based on the decision you make, you get a reward, say R2, end up in state S2, and then again you need to make a decision. You make another decision which we'll call A2, you get rewarded R3, end up in S3, you need to make a decision A3, and so forth, right? Until you get the final reward at time step, which you call, this actually was a mistake in my case, sorry about that. It's actually supposed to be time step T, capital T, yeah. Okay, so you get your final reward, RT here, and end up in some final state, ST, which we called the terminal state, right? So again, to reiterate what's happening, so you start, right, in the beginning, you're in some state, S0, right? You take an action, A0, you get rewarded, R1. Now you're in state S1, you need to take an action, A1, you get rewarded, R2. Now you're in state S2, and so forth, until you reach the terminal state ST. This is what we're looking at. Like, we are dividing every single thing that we do, every action that we make, and every time step that we make into this series of time steps and series of actions, reward, and state pairs, and so forth. So now all of these things are going to happen with some probability. It's not guaranteed that each action will lead you to the same state every time. Sometimes you take an action, it leads you to a state with a certain probability and another state with a certain probability, right? So let's kind of, sorry about that. So let's look at what I mean by this. Imagine you start in a state S0. If you remember from here, we defined S0 as our initial starting point, right? This is where everything starts and then everything follows. So yeah, state S0, you need to make a decision or an action, right? So you make your action A0, right? This is the action you make. But if this action is something like rolling a dice or something like this, or gambling of some sort, you know that you're not guaranteed to be in a certain state. And the next lecture will actually go into more detail as to how these states evolve. But for now, what you need to know is that when you perform an action, you might end up in state, what we call at time step 1, S1X. X just means that this is a different state from the one you might end up here at time step 1. So with some probability here, Px, you might end up in S1X, and with some probability Py, you might end up in S1Y. So this action, right, already you know that I am taking this action, but I might end up in this state with some probability, I might end up in another state with another probability. So already we're dealing with a lot of probabilities, and this probability will actually be the model that we need to know for the environment, and why Markov decision processes are actually kind of important to understand here. So I'll go on to say that if someone asks you, like, okay, you need to take an action, but before you take an action, as a rational person, you need to think like, oh, what's the probability that this action is going to lead me in the state that I want to be in? Maybe you want to be in S1X, but maybe S1Y is so bad that you don't want to be in it. So if Px is really high and the probability of you being in S1X, the state that you actually want to be in, is actually high, then maybe, okay, A0 should be the action you take. Otherwise, maybe it's better to take another action, right? And we'll go into this later on. But so an important thing to actually know is what's the probability of me ending up in some state, which call S prime, getting some reward R, given that I'm in some state S and they take action A. So given that I'm in S0 and I take A0, what's the probability that I end up in S1X or S1Y? That's what S prime here is. So this probability is quite important and is actually known as a transition probability. And this is essentially the model for our environment, right? This is our model. So if we know what this big set of probabilities are for our whole environment, and then we can actually start solving or developing algorithms to solve for this MTP and so forth, right? One important thing to note here is that we are just, when we're trying to estimate S1X, S1Y, or S prime, so we're trying to estimate this probability, right, of being in S prime. We are only concerned with the state S, right? But if you look at here, if we go back here, and someone asked you that what is the probability of generally ending up in state S2, right? This probability depends on what happened before R2, A1, S1. It depends on all those random variables. But we are only concerned with the very last one, which means the very last state we're in should be able to summarize all of the information that has happened in the previous state. This is called the Markovian Assumption, right? Hence the name Markov Decision Processes. You can, of course, look more into what this means, but basically, what we're disregarding, or we're just assuming that the probability of ending up in S prime or ending up in state, let's say S t plus 1, this probability will depend on what happened in the previous state, st only, and anything else before that we don't care about it. So st minus 1, st minus 2, right? We disregard all this. We just look at this kind of evolving formulation, like from st plus 1 we just concern ourselves with st, and this is a very huge assumption to make, but we'll soon realize that it's important for us to use this assumption so that for solving the problems that we're going to be solving. And I'll go into detail again in future videos of what that means, so as not to confuse you early on in these lectures, right? So this is actually quite important to know. And another property, and this will be the focus of the next video, right, that we need to know is that the summation, right, of all the states, S prime is an element of S, and all the rewards. R is an element of R, big R, sorry, of the probability of S prime comma R given S comma A. This should be equal to 1. Now, your exercise, of course, is to convince yourself why this is the case, right? Given what I just explained before. And of course, like I'm gonna go into detail in the next video of why we're actually saying this is the case, where it all came from. But for now, I'm just gonna leave it as is at this point, and we will move on to the next step, which is focusing on goals and rewards, like what we are actually trying to solve for when we're solving for reinforcement learning problems, right? So, looking at goals and rewards. So we know that the reward function is kind of like the most important thing, is what signifies our learning process when solving for reinforcement learning problems, right? And this reward function is, of course, just represented by RT, a simple numeric number that's just saying that, okay, your reward for performing this action is positive this or negative that, right? So it's just some scalar. Of course, if you look at it in the magnified view, then of course it can be a matrix and so forth, but that's not the point of this. And we said that we divided, if you remember earlier, we divided all our episodes, as we'd call them, all our events, right, into time steps, right, all the way up to some time step t, right? So this is how we had divided everything. Now, based on this, we should be able to determine what our goal is, right? We, if you remember for the first lecture, don't care about short-term rewards. So we don't care about what happens at time step 1, but we care about the sum of all rewards until time step t. So what we are trying to actually maximize is not our rewards, but rather the accumulation of rewards known as the return, right? This is what we want to maximize, and the return is represented by GT, right? So GT is equals to the summation of all rewards, RT plus 1 plus RT plus 2 plus RT plus 3 all the way up to RT, capital T, right? And this is happening at the final time step. So now that we know that, okay, what we want to maximize is the return, this happens in episodic cases, like when we can define an episode, for instance, like this event starts at this time step and it ends at this time step, right? This is what we have been assuming so far is something known as finite Markov decision problems, right? But sometimes it may so happen that there is no final time step. There's always what you call this. There's always something happening, some reward being gained. Maybe it's an infinite episode or something like this. So that leads us to a dilemma whereby we might just continue getting rewards more and more and more in the future, and our episodes never actually terminate. So that leads me to a question for you. If someone offered you $10,000 today and $10,000, let's say, in 2 years' time, right? Which one would be more valuable to you, right? And most people would probably answer that having it today is more valuable, because having it in 2 years, there's a whole uncertainty element that comes down with it. And the same goes for reinforcement learning problems. the rewards that we're gaining now are actually more valuable than the rewards that we'll get in future time steps, because in future time steps the uncertainty grows, right? So essentially what we need is to discount the future rewards, right? And what we do, like for discounting those rewards, is essentially redefining our GT to be equal to RT plus 1 plus gamma RT plus 2 plus gamma squared RT plus 3, right? All the way, right, up to gamma. This would be RT, right? This would be gamma RT minus 1, sorry. So gamma RT minus 1 will be RT. So this becomes our return, right? And the important thing to know is that gamma should be actually between 0 and 1, right? This is also an important property for gamma. So gamma is just a discount factor that actually shows that we care about immediate rewards more than we do about future rewards. And it's also important to discount our rewards in the case of infinite MDPs, because when we have infinite MDPs, then like if we don't discount our rewards, then we'll never terminate our algorithms, and you'll see why in future videos and when we go through our programming lectures, like why we're saying that this will never terminate. And you just try to convince yourself why that is for now, but we'll go through it again in the future. So essentially what we are doing is for each time step that we gain a reward, we discount it and so forth, for two reasons. One is to deal for the infinite MDP problems, and the other one is for kind of representing that we care more about rewards today than the ones that we get in the future, for example. So that's basically in a nutshell what the kind of problems that we'll be solving using MDPs and stuff. And so far I've tried to keep it quite simple, but you should have just a basic overview of what we're actually trying to do here, and the details come later, starting in the next video when we try to prove why this is the case, along with some other important concept that we'll be going through. Thank you very much.